Hello everyone, this is Shukufe Mirzai from Cal Poly Pomona, and in this lesson we are going to learn the definition of a convex set. In this lesson, first we introduce the mathematical definition of a convex set, and then we clarify this definition with an example. Mathematically, if S is a convex set and X's are any point in this set, then a point like X is also in S, where X is defined as the linear combination of these X's, where lambda, which is the coefficient of these X's in this linear combination, are positive and the summation of lambdas are equal to 1. Now, what is the meaning of this definition? Let's take a look at one example and clarify this definition. Assume we have a definition for S, for space S, and it is a collection of triplets x1, x2, and x3 with a condition that x1 is greater than or equal to minimum of x2 and x3. Any point or any triplet of x1, x2, x3 that satisfies the condition explained here, which is x1 greater than or equal to minimum of x2 and x3, falls in this space. For example, the 2.121 and 112 are both in this space. In the first point, we have x1 equal to 1, x2 equal to 2, x3 equal to 1. And in the second point, we have x1 equal to 1, x2 equal to 1, and x3 equal to 2. Now, we can check for the condition that is defined for this space, which is x1 greater than or equal to minimum of x2 and x3. If we check for this condition, we see that in the first point, 1 is greater than the minimum of 2 and 1, so this point is in space S. The same applies for the second point. x1, which is 1, is greater than or equal to minimum of 1 and 2. So these 2 points both fall in space S. So this sign here shows the 2 points belong to space S. According to the definition of a convex set that we saw earlier, if S is a convex set, then any linear combination of these 2 points should also fall in a space S. If it doesn't, then a space S is not a convex set. But if the linear combination of these 2 points falls in space S, there is always chance that this space is a convex set. Now let's look at one linear combination of these 2 points where satisfies the condition that we earlier set. For example, let's look at this linear combination where lambda 1 is equal to 1/2 and lambda 2 is also equal to 1/2. So the summation of these 2 lambdas, lambda 1 and lambda 2, are equal to 1, and each of these lambdas are positive. So the condition that we defined earlier for this linear combination are met. The question is whether this new point falls in space S or not. Now let's check for the condition of the space. If we look at this condition, we see that this condition is not met because the minimum of x2 and x3 is 3.5 and it's greater than 1. So the condition defined for this space is not satisfied here. So S is not a convex set. Please note that this is enough for us to conclude that S is not a convex set. Whereas if this point belongs to space S, this is not enough evidence to conclude whether S is a convex set or not. Now, since the condition is not satisfied, we conclude that this point doesn't belong to space S, and hence S is not a convex set. There is another definition which is more intuitive and visual for defining a convex set. According to this definition, a set of point S is a convex set if the line segment joining any pair of points in S is wholly connected. What is the meaning of this definition visually? So look at this example. If I connect any 2 edges in any of this figure and the line totally falls within this space, then the space is considered as a convex space. Otherwise, the space is not a convex set. Let's look at the first example. If I connect two edges in this figure, you'll see that there is a part of the line that falls out of the space. Hence, this space is not a convex set. If I look at the second example, you see that by connecting any two edges in this space, the line totally falls in this space, and hence this space is a convex space or a convex set. We can test the condition in the following example as well. As you see in the first space, the part of the line falls out of space, so it's not a convex set, whereas in the second figure, the whole line falls inside the space, so this space is a convex space. And the last figure, we can connect a line which falls out of the space, so it's not a convex set. With this, our definition of a convex set has concluded. Please refer to your blackboard for your assignment. Thank you.